Oh, Joe, you're here. You missed my morning stream. Okay. For those that are watching now and potentially later, this is AP Stat Course Review number 2, which, again, I'm going to be going through some free response questions. As I'm going through these questions, if people have requests, As to the types of problems that we review, please by all means put those requests into the chat. I have a slew of problems, free response questions that we could cover in this topic. Otherwise, I will just pick more free response questions from the stack of cards that I have, very similar to what I did yesterday. And we will go from there. So, just to make sure, that's a good one. Here we go. Let's start with this one. And I'll zoom in on the card as always, just so we have a good idea as to what we're dealing with. Come on, card. There we go. A senator's approval rating stood at 76% before she took a crucial vote. Her staff believes the rating is still around 76%. To confirm this, how large a simple random sample should they sample to obtain a 90% confidence interval estimate with a margin of error less than or equal to 3%? Now, I'm going to write down some information, then I'll zoom back out. They believe they're at 76%. That is the belief. And they're going to take a 90% confidence interval. Sorry, 90% confidence interval. And they want the 90% confidence interval to be less than or equal to 3%. So let's see here. I'm just writing out a formula, and then I will zoom the camera back out. There we go. Come on, you. There we go. Zooming back out. What is going on here? Oh, Mr. Video Call. Anyway, so I'm looking at this particular problem. And we have a certain belief of 76%. There are a couple different ways that you could go about this problem, trying to find out, okay, what sample size am I going to get? Typically speaking, confidence intervals are attempting to capture the true proportion. Typically, we don't know what that true proportion is. But according to the problem, the staff believes that 76% is the number. So this is one of those strange circumstances where we're trying to find a sample size, but the p hat q hat, although we don't actually have a sample, we're going to have to put at 76% and 24%. For the 90% confidence, just as a reminder, 90% confidence, we are excluding the outside 10%, split in half, which means we're at the 95th percentile. Now notice I did Z, I jumped straight to Z, because if you're dealing with categorical data, if you're dealing with proportions, you're going to have to worry about Z and not T. So let's do an inverse norm of 0.95. We get 1.645. 0.03 greater than or equal to 1.645 square root 0.76.24 over n. Solving for n, I'm going to take my calculator in a moment. I'm going to divide by the 1.645. I'm going to then square. I'm going to move the n over. I'm not going to write this down, but I'm going to move the n over and then have to divide by the crazy decimal that I get. So that's going to have to be n is greater than or equal to, once I move that n over. Let's see what happens. 0.03 divided by that squared, moving everything over. 0.76 times 0.24 divided by that answer gets me approximately 548.3. So you're looking at surveying approximately 549 people. Because you don't want to round down in that case. You want your margin of error to be less than or equal to that 0.03. Part B. Bring this right here. Here we go. Her staff randomly samples 600 people. Now the sample's actually being taken. And finds 440 people approve of the senator's job performance. Is there evidence? Now, that statement unto itself implies that a test should be run, but is there evidence that the rating has changed from 76%? Perform an appropriate statistical test. Now, since we're going to perform this appropriate statistical test, we are going to have to go through the full hypothesis test for Part B, where the null hypothesis is the belief that p is still equal to 0.76. And the question is there evidence that the rating has changed, which means that my alternate hypothesis is going to be not equal to 0.76, making this a two-sided test. Now, assumptions and conditions, I'll just shorthand some of the stuff right here. 600 is large enough sample. You could do, now, because the sample was taken, you could take it as the expected number, because we do have an assumed number here, 0.76 times 600, 0.24 times 600, in order to find the expected number of successes, expected number of failures. You could say 600 is less than 10% of people who could eligibly vote for the senator. That the population of people who could vote for the senator, something along those ideas, less than 10% of voting population. And the fact that it was a random sample implies that whether or not you believe you approve the senator or not, that your opinion is independent of anyone else's opinion. But we could run a one prop z-test in this regard. A one prop z-test. Let's see. One prop z-test. Oh, goodness gracious. Where 0.76 is the assumed. They did 440 out of 600 in the sample. We're doing not equal to. If you calculate that, you get a p-value of 0.126. Did they get the same on the back of the card? Yes, they did, of course. This is a two-sided test, so if you did run a normal CDF going in one direction, you would just have to double it in order to get that particular p-value. But this p-value was too large. We would fail to reject the null, not enough evidence to suggest approval rating has changed. There is not enough evidence to show that the approval rating has changed. I'm going to change markers. This one's dying on me. Come on. Excellent. So let's look at Part C. In Part B, suppose the staff suspects that the rating has gone down. Is there evidence that the approval rating has slipped down from 76%? Perform an appropriate statistical test. Now, for Part C, it would pretty much be the exact same kind of test. The one main difference for Part C would be that your null hypothesis would still be 0.76, but your alternate would be less than 0.76 because of the context of what they're trying to find out. They're now trying to do a one-sided test. Now, in this instance, well, it would basically be this p-value except cut in half. I'll show you. The 0.126 is going to be cut in half if I run a one prop z-test, but instead do less than for the alternative. Calculate. You can see that that p-value would now be 0.063. Now, is this evidence to show that the approval rating has slipped? Well, it depends on what your alpha level is. They never set what the alpha level will be. we could fail to reject again based on an alpha level of 0.05. Based on an alpha level of 0.05, we could say there's not enough evidence to suggest that the approval rating has slipped, but there would be enough evidence if our alpha level was at 10%. Remember, raising the alpha level to 10% reduces the beta, or the chance of making a type 2 error. So there's really a balancing act there. Let me show you what the back of the card actually said. The back of the card said P.0629, which is what we got, and thus there is some evidence, at least at the 10% level, that the senator's rating has slipped. You could say something along those lines. You should always specify what your alpha level is, especially if the problem doesn't say, because that justifies the answer that you are purporting to get. Now, part D, they're asking if the answers in B and C are contradictory. Well, based on what the card got, yes, they are. No, I shouldn't say yes, they are. I'm saying the conclusions are contradictory, but the rationale is not contradictory at all. It's really not. There is no contradiction. The tail probability of a test statistic is doubled. Thus, what might be a small enough tail to reject for a one-sided test might no longer be small enough doubled for a two-sided test. So yeah, there is no contradiction in the sense of a mistake being made. There is no contradiction in terms of the proper conclusion that should be reached based on the question that is being asked. But if you did fail to reject in one regard and reject in the other, then yes, you're getting contradictory conclusions, but the mathematics are absolutely correct. So, I mean, they're saying there is no contradiction, and I agree with that. It's a point of perspective as to what you're looking at. Okay. Let's try another one. I want to get to one that... no, not that one. A lot of them are asking for that sample size thing, and we've already done that sample size thing like a bunch of times over and over and over. This is a pretty good one. This is probability. Yeah, let's do the probability one. Let's do the probability one. Let's zoom in on the card. Come on, zooming in on card. Okay. Dice A has 2 5s, 3 3s, and 1 1 on its 6 faces. Dice B has 2 2s, 4 4s, and on its 6 faces. Both dice are fair. Each player simultaneously rolls one of the dice, and the winner is the player with the higher number showing. If you want to win, would you rather roll die A or B? And then if the winner receives whatever shows on our die, what is the expected value for one roll to each player? Well, first, let me write down some information for die A and die B, and then I'm going to zoom back out. So for die A, there are what they call 2 5s, 3 3s, and 1 1. On die B, there are 2 2s and 4 4s. Okay. Let's zoom this thing back out. Come on, you. Why can I never zoom back out properly on this thing? Whatever. Okay. So that's what we got. So on die A, it looks like... I'm trying to do a little probability chart here. 1 out of 6 chance, a 1/2 chance, and a 1/3 chance of getting these particular results. On die B, it looks like you have there's only 2 options here. And was that 2 out of 6, 1/3, and 4 to 6, which is 2/3. Okay. So here are the probability features. Now, in terms of if you want to win, would you rather roll die A or die B? You're going to have to justify your answer. You can give a correct answer of die A or die B, but you'd have to justify what that answer is. The back of the card, that's interesting. I'm not going to say what it is just yet. I was expecting either die A or die B to win, but let's just figure out what this thing is going to be. If you want to win, what would you rather roll? Well, if you're going to do expected value, I'd multiply, I'd multiply, I'd multiply, and then I'd have to add all three of them up. Let's see what we get here. 1/6 plus 3/2 plus 5/3. We're good. Oh no, my calculator fell and it's all over. Anyway, by the way, there's a couple different ways to go about this, but let's just see what happens here. 3 1/3 on average. Come on, calculator. There we go. 3 1/3 on average. I might be contradicting what the back of the card says, but let's just see what happens. If I were to multiply here, I'd get 2/3. Multiply here, I'd get 8/3. Add them together, I get 10/3, which is exactly the same. This is not exactly what the back of the card has in terms of work. But what I have just shown is the expected result on die A, on average, would be a number at 3 1/3. So if you had to average out your results of rolling die A and getting 1s and 3s and 5s, in the grand scheme, in the rolling it like 1,000 times, if I had to find an average value, it'd be 3 1/3. If I did the same thing for die B, rolled it 1,000 times and took an average, 3 1/3. The answer to question A, if you want to win, would you rather roll die A or die B? They have the equal chance of winning. And you can see that on the card right here. On the card right here, they don't go through exactly the math that I did. They talk about the probability that A wins versus the probability that B wins, and they have an equal chance of winning. The players have an equal chance of winning, which is, I found the expected value of those dies to be exactly the same. It's the same conclusion. Same exact conclusion. Now, in terms of die A winning, die A could win if rolls a 5 or rolls a 3 and die B rolls a 2, which is why the probability that A wins, if they roll a 5, they win no matter what. Or they could roll a 3 and die B has to roll a 2. If you figured out this calculation, it ends up being 1/2, which means that A has a half chance of winning. At this point, pretty much die B has a half chance of winning, or a 50% chance of winning, but you could also do the calculation like that as well. This is what the back of the card is basically trying to say. Die B would win if it rolled a 4 and die B rolled, well, a 3 or a 1, so this is going to be a little bit more complicated. Yeah, well, 3, or die B rolled a 4 and die A rolled a 1, or die B rolled a 2 and die A rolled a 1. If you did that calculation, and I'll actually show that right here. Can you see the rest of that? You can't really see the rest of that. There we go. I'll show that calculation here. It's going to end up being 1/2, 2/3, 1/2, 2/3, 1/6, 1/3, 1/6. Boom. Oh, what did I type in wrong? Forgot to put a plus sign. Forgot to put a plus sign right there. 0.5. So that's what this thing ends up being. It's quite interesting in the fact that oh, sorry, I'm getting messages on my phone for some reason. It's really weird. But anyway, it ends up being 1/2 as well. So the question that they ask in response to that, you can see that in part B right here. If the winner receives whatever shows on his or her winning die, what is the expected value for one roll to each player? See that if they win, sorry, I'm looking at what they did in terms of if they win. Because if they win and they win whatever shows on their die, it's not as straightforward as the expected value that I got in part A. If the winner receives whatever shows on her winning die, what is the expected value for one roll to each player? And what they did here, they showed... Okay. I'm going to compare this to what they got right here. I'll zoom in a little bit here just to kind of show you what they're doing. Too much. What they did right here with this calculation, this is the expected value of A, meaning 5 times 1/3 chance and a 3 times 1/6 chance in order to get like an expected value of winnings. But then for expected value of B, they're doing this weird calculation. Okay, in order to get that expected value. That one's a bit more extreme. Basically, it's like they would win this percent of the time, and then you would have to multiply it by what shows on the die, basically. If B wins, there's a 1 in 18 chance they would win by rolling a 2, which is this 1 out of 18. Oh, you can't see it. Move that over here. There we go. That's this 1 out of 18 right here. And they would win with a 4 out of 9 times. That's these two right here. And then you would get like an expected value or something like that. I don't know if that would be dollars or whatnot. But yeah, that's what the question's really going for. It's a very strange question. Expected value. Love it. Let's see what else we can do with this. Okay, yeah, let's talk about this one. This one's going to be a bit more in terms of, not in terms of calculations, but in terms of verbiage. There we go. High cholesterol levels can be reduced by low-fat diet or medication. Researchers would like to test the effectiveness of a new medication and to note whether the effectiveness, if any, is enhanced by diet. 100 volunteers with high cholesterol levels on no special diets and not on medication are recruited for a study. Conclusions will apply to what population? Let's go through a piece at a time. Conclusions will apply to what population? Well, they had 100 volunteers with high cholesterol levels, not on special diets and not on medications. It may be very specific, but that's the population that you really have to focus on. You can't apply this to people on low cholesterol levels or people with special diets or people on medications. It's a very niche group of people. The back of the card, conclusion will apply to non-dieters with high cholesterol levels who are not taking medication. Clearly. I just want to get that wording in. But unfortunately, you can't make any conclusions about people outside of that particular demographic. Part B. Explain how you would design a completely randomized experiment. Well, you have 100 volunteers, and they're saying, okay, it can be reduced by a low-fat diet or medication. Now, this is something where you have to be very careful with how you split up these groups. Now, without reading the back of the card, I'm just going to give you what my take on this particular card is. They're saying low-fat diet or medication. You cannot conflate the two. What would potentially be helpful is if you took those 100 people and you actually split them up randomly into 4 groups. Since those 100 people are not on special diets, not on medication, and have high cholesterol, you can split them into 4 groups, have one group commit to a low-fat diet with no medication, have a second group commit to medication, but no low-fat diet, just regular diet or whatever the heck they're doing, or stay the same. A third group that does both, which could potentially be helpful. You could compare both against just the low-fat diet or just the medication. but then you need a fourth group that's doing neither of those two. You need a control group as well. You could randomly split them into each of these four groups, have them run through the experiment, and then compare their results. Back of the card. Let's see. Again, I didn't read the back of the card. I was interested in what it says. The design should incorporate random assignment of the volunteers to four treatment groups. Hey, I did it. Medication and diet, medication and no diet, placebo and diet, and placebo and no diet. Ah, interesting. That is a much better way of doing it than I described. And a measurement and comparison of cholesterol levels. What they're suggesting on the card is something better than what I did. In terms of a control group, you still want them to believe that they're going through the experiment. The medication could be a placebo. They could be led to believe that the medication that they're given is real, but it ends up just being a placebo, and then you could see whether or not there's a placebo effect, or whether just the brain is stronger than whatever medication they're getting, something along those lines. It's pretty solid. Yeah. But they do go with the four group idea, which you could totally do. How about you incorporate blocking, and for what purpose? Now, blocking is similar to that of stratified sampling. In stratified sampling, you would break groups up by some characteristic where within each strata they have some sort of homogeneous connection to each other. For example, if you were to survey 100 high school students, then you could split them up by boy and girl, if that was helpful in terms of comparing their results. Or you could survey them and split them up by grade level, if that was helpful in comparing their results. So in terms of blocking, what could we block by in order to potentially get some better information? There's a bunch of different answers you could do to this, as long as it is reasonable within the context of the problem. Let's just see what the back of the card says. There are many possible answers. I didn't even read that part. There are many possible answers, but each should be explained in the context of the problem. For example, you could block by gender or age, because men versus women or old versus young might respond differently to medication or diet. In any case, give the scheme of first splitting volunteers into separate blocks and then randomly assigning subjects in each block to four different treatment groups. Yes. It doesn't necessarily matter what answer you give, as long as that answer makes contextual sense. You can go simple with age or gender, or you could do something a bit more complex, but that's completely up to you. How might blinding be incorporated in the study, and for what purposes? Blinding is when there's two types of blinding, I should say. There's blinding on the part of the person receiving the treatment, like they don't know that they're receiving the treatment or not, something along those lines. But there's also the other side of blinding, which is the person doing the evaluating. Now, they're looking at high cholesterol levels, so it's not a subjective evaluation, it's an objective evaluation. You're looking at the cholesterol levels and whether or not they've been reduced. So the person doing the evaluating does not need to be blinded. But it could be helpful, obviously, if the person participating in the experiment was blinded. In fact, they probably are, if they are receiving the placebo. How might blinding be incorporated in the study, and for what purpose? Blinding is incorporated through the use of a placebo. If there is a possibility, some volunteers might be able to subconsciously influence their cholesterol levels if they knew for sure they were taking medication and thus expected results. This would be a one-sided blind experiment, I should say, is the phrasing I'm going for. If you want it to be two-sided, then the evaluators have to be blinded, but they don't have to be, because they're measuring cholesterol by some computer device or something along those lines. A lot of proper wording is what the answers are really looking for in this regard. I do kind of like that one. All right, let's see what this one does. A Major League Baseball scout is checking out a minor league pitching prospect. Using a timer, finds the average speed of his fastball to be 92 92.3 miles per hour with a standard deviation of 2.3. Assume the pitcher never tires and there is a consistent normal distribution of fastball speeds. Now that would be a very important assumption, obviously, because if you didn't assume that, obviously people would tire over time, blah, blah, blah. And he's telling you to assume normal distribution so you don't have to check assumptions or conditions, thankfully. Would you check the timer if it registered 95 on the next fastball? Explain. Now, I think what they're trying to basically say is 95 miles per hour unusually high? And if that were the case, then you would give some explanation as to what is considered unusually high, and you could say because of the normal distribution, you can say 2 standard deviations above the mean or below the mean would be unusually high or unusually low. Now, 2.3 is the standard deviation. If you were to go, you could do this in one of 2 ways. You could do 92.3 plus 2.3 plus 2.3. That would be 2 standard deviations above, which 95 miles per hour is within. Or you could do data point minus average divided by standard deviation, 1.17. Clearly, that z-score is not unusual. Definitely not unusual. Back of the card, not unreasonably, I can't see it, not unreasonably probable. Oh, they went farther than I did. They found the z-score, but then they found the probability of that happening. You don't have to go that far. You could just go by the definition of within 2 standard deviations. I mean, if you wanted to find the probability, there's a 12% chance of that happening, which clearly anything under 5% would be considered unusually low. Or under 5% cause to reject whatever null hypothesis you're going with. Part B. Would you check the timer if the next 30 fastballs average 95 miles an hour? Now that is something a bit more complex. Because if you're talking about a sample now, a sample of 30 fastballs averaging 95 miles an hour, now you're talking about a sample distribution. Now you're talking about the fundamental theorem of statistics. Because with the fundamental theorem of statistics, the larger the sample size, the more normal the sample mean distribution is supposed to be. Or more specifically, the more samples that you run, the average should be closer to the expected or assumed mean. So this is something that we're going to have to do a little bit of a calculation for. So let me zoom back out. There we go. Now, we are looking at an assumed mean of 92.3 and an assumed standard deviation of 2.3. Yeah, come on, you. Okay. Now let's look at the number of standard deviations away from the mean. This could be if they found an average of 95 miles an hour given a sample size of 30. Now, I believe it was chapter 17. It was sampling distribution, sampling distributions or something. I can't remember the name of the chapter exactly. But there was a particular calculation that you could do in order to find a proper z-score of that sample average. Now, in this case, it'd be 95 minus 92.3, just like before, but this time it'd be over 2.3 divided by the square root of 30. The larger the sample size that you get, the less likely you're going to deviate far from that accepted mean of 92.3. So if we did that calculation, I'll do that over here. 95 minus 92.3 divided by parentheses, 2.3 over the square root of 30. You find a z-score of 6.43. Now, that many standard deviations away from the mean, incredible incredibly unusual. The reason why we had to do this calculation, the reason why we had to put it over the square root of 30 is because now you have a sample average and not just a single pitch. Let me zoom back in on the card right here. You can see what I'm referring to. In part A, would you check the timer if it registered 95 miles an hour on the next fastball? That's one pitch. Getting one pitch at 95, that's not unusual. Z-score was like 1.17. But getting 95 miles an hour on the next 30 pitches on average, that is incredibly unusual considering what this guy is supposed to average and supposed to standard deviate, whatever that phrasing is. So you can see the back of the card right here. They go into much more detail, but ultimately you definitely should answer the question. The timer should be checked for part B, but it's not unusual for part A. Something along those lines. Let's see what we're gonna do next. Chi-squared is not gonna be on this test. Okay. This could work. Let's do this one. More reading in this particular question. Just a little bit. There we go. A guidance counselor conducts a study to determine the effect of caloric intake at breakfast on alertness in first period classes. She interviews a simple random sample of 20 students who claim to eat under 1,000 calories at breakfast and a simple random sample of 20 who claim to eat over 1,000 at breakfast. In each group, she measures alertness on a standard scientific scale, whatever that means. Part A. Explain why this is an observational study and not an experiment. The main difference between an observational study and an experiment is a treatment. A treatment is a manipulation of some sort, something that is introduced into whatever group you decide to do. Now, in this case, there's no treatment. You're just interviewing two different random samples. So, yeah, it's not an experiment because there's no treatment. There's no manipulation. Part B. Give an example of a possible confounding variable with an explanation in the context of the study. Now, for these types of questions, obviously there's a number of different ways that you could potentially go. A number of different ways. But you need to answer it in the context of the problem. So, confounding variables, something that could confound the results. Let's just go back into the wording of the question. They conduct a study to determine the effects of caloric intake at breakfast on alertness in first period classes. She interviews that many students, blah, 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 blah. She measures alertness on a standard scientific scale. Well, right off the bat, something that immediately pops out to me is confounding variable. Well, how much sleep did they get? You know, these students, perhaps their alertness in first period classes is not necessarily based on how many calories they consume at breakfast, but perhaps on how much sleep they got the night before, or at what time they went to sleep the night before. Something along those lines. There's a lot of different possible confounding variables, but that's one that immediately pops out to me. Let's see what the back of the card says. No treatment, as we said. There are many possible answers for Part B. For example, it's possible the students are those who sleep in late and have to rush to school without eating and have not fully awakened during first period. Yeah, depending on how much sleep they get. It's a good part to see. If the students who eat over 1,000 calories test higher on the alertness scale, is it reasonable to encourage all students to eat a larger breakfast? No! Absolutely not. If the students who eat over 1,000 calories test higher on the alertness scale, is it reasonable to encourage all students to eat a larger breakfast? No. Just because you found a correlation does not mean that you have causation. Correlation does not equal causation. I think the back of the card even said that. I just glanced briefly. No, cause and effect conclusions cannot be drawn from observational studies. They don't say correlation doesn't equal causation, but there would be a correlation based on this observational study. You're going to have to conduct an experiment. D. How could the counselor design a related experiment to study caloric intake at breakfast with alertness in first period? Now, it's going to be very tough to do so because you would actually have to not ensure, not guarantee, but you would have to have some kind of implication that the level of sleep that they get is not a factor. If you were to randomly assign them to groups, if you had like a number of students, 20 and 20 of 40 kids, if you were to randomly assign these 40 kids to groups before you conducted the experiment, then that would hopefully balance out the imbalance in the amount of sleep that they get. But then you could have half the group commit to an over 1,000 calorie breakfast and the other group to an under 1,000 calorie breakfast. Do that for an amount of time and then eventually rate their alertness on that scientific scale again. Let's see what the back of the card says. There we go. Randomly select a group of students who are told they must eat under 1,000 and randomly select another group who told they must eat over 1,000. Compare alertness levels in first period class. Yeah. You see, the level of sleep that they get hopefully would be balanced out by randomly assigning them to each group. That is the hope. Obviously, it's very difficult to control how much sleep one group gets over another. Yeah. That random assignment is key when creating an experiment. Random assignment is key. Let's see what else we can do. I don't like that one. Ooh, that's fun. That one's weird. Okay. Yeah, let's totally do this one. Okay. So something that is common every year is that they always have like a question that asks you to calculate something that you've never done before. It's some random, like, here's the rules as to how this calculation works, now do it. That's what this thing is basically doing. During the 2006 NFL postseason, the 12 participating teams scored the following number of passing touchdowns. The trimean is defined as Q1 plus 2 times the median plus Q3 over 4. Compute the trimean for the above data and show your work. Well, thankfully, they've already put the data in order. If you wanted to, you don't actually have to do this, but if you wanted to, you could input that data into a list, which I just did, run a 1var stat, and it would give you the Q1 median and Q3, or, which is 1, 2, 3, or you could just figure that out by hand. That's up to you. Parentheses, 1 plus 2 times 2, plus 3, the whole thing over 4. Clearly, I don't know, I'm just showing you the work there, but you get 2 for the trimean. The trimean is 2. What was the rest of the data? I just wonder. The actual mean was 2, and the median was 2. Everything was 2, whatever. The mean trimmed 50% is computed by trimming the upper 25% of the scores and the lower 25% of the scores, and computing the mean of the remaining scores. Compute the mean trimmed 50% for the above data and show your work. Well, if you were going to trim the above 50%, that would be, I'm sorry, the above 25%, that'd be everything above the third quartile. If you were going to trim everything below the 25%, that would be everything below the first quartile. Let's just see what it does here. So there's 12, there's 6, 1, 2, 3. So yeah, there, right here, would be everything below the first quartile, and everything here would be above. So you'd basically be taking the middle 6. So if you were going to take the middle 6, that would be 1 plus 1 plus 2 plus 2 plus 3 plus 3, which clearly, why am I even doing that? But they want you to show your work for that. If you're ever going to show your work, then clearly that's something that you would do right there. Seems like a really inane problem. Am I missing? No, they just really want you to show that work. The trimean is 2, and then Part B is 2. It's so weird. So then more generally, to compute a trimmed mean, you remove some of the higher and lower scores and compute a mean of the remaining scores. In what way can the median be considered a trimmed mean? Well, if you're removing everything above the median, you're removing not exactly 50% of the data, but like just under 50% of the data. And if you remove everything below the median, it's just under 50% below that you're removing. So that in that sense, it's a trimmed mean. What does the back of the card say? The median trims the upper 49% and the lower 40. Oh, plus. Yeah. Okay. That's exactly what I said. Just used 49 plus instead of just under 50. In general, what advantage might both the trimean and the trim mean have over the standard mean? There's a bunch of different ways. The trimean and the trimmed mean are resistant to extreme values. The mean is sensitive to extreme values. Yeah, that makes perfect sense. Same thing with the median. Typically, we do the median like the central measure of central tendency. The median is not sensitive to outliers. But these two brand new calculations that you've never seen before in AP Stat, the trimean and the trimmed mean, you've never seen them before in AP Stat, but they are also not going to be sensitive to outliers. That's pretty solid. All right. Let's see what else we can do. Oh, fantastic. This is a good one. Let me zoom out just a little bit so we can see this one a little better. There we go. A clothing manufacturer wishes to test which of two sewing machines leads to greater production. The workroom consists of 8 large tables, and they plan to have everyone at a given table use the same machine. On one side of the room are windows with a pretty view, which, as a side note, could affect production level. And on one side is the floor's manager's desk, which could also affect production level. Think about it. Logically, without reading the rest of the question, if you're closer to the window, it could either be something where you're distracted by what's outside, or you could say that, well, it looks nice outside and that's going to help me perform my job better, something along those lines. Whereas, if you're close to the manager's desk, you might work a bit more diligently because you're afraid you're being watched, or your work might suffer because you're afraid of the authoritarian, employer on top of you, whatever. So both of those things could potentially affect the production level, either positive or negative. So they're probably going to come into play. Part A. Suppose you decide to block using scheme A below. Okay? One block is white, one block is gray. How would you use randomization, and what is the purpose of randomization? Okay. The purpose of randomization is to reduce bias. That's one of the biggest things, just without the context of this problem. Randomization is supposed to reduce bias. There are 2 different types of sewing machines. So they're putting each block represents a sewing machine, I'm assuming. The workroom is an 8 large table. The plan of everyone at a given table use the same machine. Okay, that makes sense. Yeah. And what purpose is randomization? How would you use randomization? Well, I mean, you could randomly assign employees to a table. You don't have to randomly assign the sewing machines. I mean, you could if you wanted to, but since each block is going to be using the same type of machine, like let's say machine A or machine B, machine A would be all here, machine B would be all here, etc. Randomization of sewing machines doesn't matter, but randomization of employees absolutely does. You want to reduce bias in any way possible. Let's just see what the top of this card said right here. I'll read the bottom later. In each block, 2 of the tables will be randomly assigned to receive one of the machines. Okay, yeah. Well, that's randomization of the machines. Not that you would pick like, oh, machine A goes to the gray and machine B goes to the white, but you'd randomly assign which one goes to which, while the remaining 2 tables in the block will receive the other machine. Okay. Randomization of machines to tables within each block should reduce bias due to confounding variables associated with the tables that might be related to productivity. In particular, the randomization blocks in Scheme A should even out the effect of the distance the tables are from the manager's desk. Interesting. Ooh. Okay. Am I reading this? I want to make sure I'm reading this properly. The workroom consists of 8 large tables. They plan to have everyone on one side of the room. Okay. I see what they're saying now. I see exactly what they're saying now. Again, part of the issue with a lot of these problems is deciphering exactly what the question is actually asking. They're suggesting in Scheme A that they block in the following way. And the reason why they're blocking in the following way is they're trying to minimize the effect of the manager's desk. And they're trying, oh no, they're trying to see, okay, those by the window, those not by the window. Oh, it's so weird. Okay. So they're ignoring the manager's desks for Scheme A. They're ignoring the manager's desk and they're looking at, okay, let's put these by the window and these not by the window. And then they're going to randomize it. So they're going to have the 2 machines and the 2 machines randomized and then the people randomized. That's so weird. I love it. Comment on the strength and weakness of the Scheme A as compared to the blocking of Scheme B. Okay. With Scheme B, again, that's proximity to the manager's desk. Scheme A was in relation to proximity to the windows. The Scheme A creates homogeneous blocks with respect to the windows. There we go. Scheme B creates homogeneous blocks with respect to the distance from the manager's desk. Randomization of machines to tables within the blocks in Scheme A should even out the effects of the distance to the manager's desk, while randomization of machines to tables within blocks in Scheme B should even out the effects of window exposure. I gotcha. Okay. Again, this is an awkward type of wording to this problem. And I'll try to block them off like this. I'll cover them up. So I'm only talking about Scheme A for a moment. In Scheme A, they're basically saying, okay, first block, you guys are going to be close to the windows. This is the gray block. You're going to be close to the windows, and 2 of the tables will get 1 machine, and 2 of the tables will get the other machine. And then on the white blocks, you're the block that is away from the windows. They're blocking in that fashion in order to see if proximity to the window would affect their production level, something along those lines. Whereas in Scheme B, they're ignoring the windows, and they're basically saying, okay, we're going to block you by proximity to the manager's desk. And if you're in the gray block, you're far from the manager's desk, and then 2 of the tables will get 1 machine, and 2 of the tables will get the other machine. And then in the white block, they're, again, 2 and 2. But you're close to the manager's desk, so they're blocking by proximity to the manager's desk, but they're not taking into account the pretty view. So if they're talking about comment on the strength and weakness of Scheme A as compared to Scheme B. So, and again, this is the context of the problem, and this is more of a subjective statement that you can make as to which one you believe is stronger than the other, but you could talk about the strength and weakness of each individually as well. So, for example, in Scheme A, the strength being the fact that they are comparing whether or not the pretty view affects production level of these machines, but they're not taking into account the proximity of the manager's desk, which could confound the issue. But then in Scheme B, the strength would be they are taking into account the manager's desk, but they're not taking into account the pretty view. Oh, I love problems like this. They're so super fun for me. Okay. we're going to wrap up with this one today. And I'll have to zoom out and actually do this calculation. It's a probability problem where they don't give you much context, but you're going to have to noodle out exactly what the question's asking. This will be the last question today. Suppose a police breathalyzer unit will correctly test positive for 98% of legally drunk drivers, but will also give a false positive reading for 3% of drivers whose actual blood alcohol concentration is under the limit. If 5% of late Saturday night drivers are legally drunk, and an officer arrests 2 drivers with positive readings, what is the probability that exactly one of the 2 is guilty of driving drunk? Oh, sorry, I just saw the question in the thing. Pretty much, to answer your question, 45 minutes, 2 questions, I believe it is. And in terms of calculators, I mean, obviously, I would make sure that you have some form of a calculator, just in case. But I believe if they're going to give you calculations like you're thinking of, they would be a bit more basic than some of the more advanced calculations that you would do for AP Stat. But yeah. Hope that answered your question. I gotta finish this one up though. Sorry, no fault to you. I lost my train of thought on the problem. Oh goodness. Okay, so let me zoom back out to a piece of paper, and we'll write out some of this information. So it says that. I'm going to make sure I write out the proper information. It says 5% of late Saturday night drivers are legally drunk. Legally drunk, obviously. So we'll put not drunk at 0.95, just for the sake of argument. Legally drunk, legally sober, whatever. Anyway. But then they say that suppose a police breathalyzer unit will correctly test positive for 98% of legally drunk drivers. Meaning, given that they are drunk, the probability that they'll get a positive test is 0.98. I'll go back to the wording of the question in a minute. I'll hold the card up so you can see the comparison. But then it says, I guess you could then say that they'll get a negative test, given that they're drunk, is 2%. That may come in handy in a little bit. But then the probability of getting a false positive, meaning that the person is actually not drunk, given that they're not drunk, and I'll show you the comparison of this in a minute, that they'll get a false positive is 3%, which means a positive test, given that they're not drunk. That's a mistake, obviously, but there's a low chance of that happening, which means the probability of getting a negative test, given that you're not drunk, is 97%. Let's look at the comparison on the card in a moment. I'll hold the card up to the camera so you guys can see exactly what I'm referring to here. There we go. It says, suppose a police breathalyzer unit will correctly test positive for 98% of legally drunk drivers. That statement, given that they are drunk, the probability that they will test positive is 98%. That's what this calculation is right here. Given that they're drunk, that they'll test positive. Then, but will also give a false positive reading for 3% of drivers whose actual blood level or blood alcohol concentration is under the limit. So that second statement for 3% is, if you were to boil it down to basic words, given that they are not drunk, the probability that they'll get a false positive, meaning just that they're positive, is 3%. That's what this calculation is right here. Given that they are not drunk, that they'll get a positive test. Which, by the way, that's the 2% came from just the not a positive test but a negative test, and the 97% came from not a positive test but a negative test as well. If 5% of late Saturday night drivers are legally drunk, so basically 5% are drunk, 95% are not drunk, and then an officer arrests 2 drivers with positive readings. We'll deal with the 2 drivers in a moment. We will deal with the 2 drivers in a moment. But for now, I want to draw a little bit of a probability tree. Being drunk is 0.05. Being not drunk is 0.95. Then, given that the person is drunk, they'll get a positive test 98% of the time. They'll get a negative test 2% of the time. Not drunk, they'll get a positive test, which is a mistake, clearly. Which the negative is a mistake too, but this one is 0.03. And that they'll test negative, which is correct. Not drunk and negative 97% of the time. Okay. It's going to be helpful to conceptualize all this information with the given statements and whatnot. All of that information coming off of the problem. Now, the question that we are trying to figure out, they want to know the probability that exactly one of the 2 drivers is guilty of driving drunk. That sounds like a binomial problem to me. But we are going to have to calculate some stuff first. Yeah, we're definitely going to have to calculate some stuff first. Okay. What we need in order to answer this question, first, we need to find the probability of being drunk given that there's a positive test, which reverses a few of this stuff, or a few of these stuff. It reverses this one right here. Not positive test given drunk, it's drunk given positive test. Now, the best way to go about this, we need to find the probability of both divided by the probability of the given event, which is getting a positive test. Drunk and positive, if we were to multiply the 2 of those together, drunk, positive, you get 0.049. That's going to be the top of my fraction. Getting a positive test, you could either get one while being drunk, or you can get one while being not drunk. There's a possibility of that happening. 0.95 times 0.03 is 0.0285. On this probability tree, you could be drunk and get a positive test, or you could be not drunk and get a positive test. If you add the 2 of those together, that's the bottom of my fraction. 0.0775. 0.049 divided by 0.0775 gives me approximately 0.632, I guess you could say. I'll go 2.3. I don't know. Now, why do I need that? Well, again, let's go back to the question. 2 drivers are arrested with positive readings, given that they are positive readings. What is the probability that exactly one of the 2 is drunk? Given that they have a positive reading, the probability of being drunk, and this is just for one of them, is this probability. Independently of each other, each of those 2 drivers has a 63% chance of being drunk, given that they had a positive test. Now the question is asking, what is the probability that exactly one of the two is guilty of driving drunk? This is a binomial problem. They want to know the probability of one drunk out of two given a positive test. This is a binomial problem. There's a couple different ways of going about this. One way of thinking about it, binom, I should say, PDF, because it's exactly 2 trials, 0.6323 chance of success, or what you're looking for, and getting exactly one drunk out of those two. Binom PDF of that calculation. Let's see if it actually matches the back of the card. Binom PDF 2, 0.6323, 1. Nice. The back of the card did not do that. They did this. They did the probability of exactly one success in 2 trials, 2 times that, because it could happen in either order. It could actually be drunk, not drunk, or not drunk, drunk. But they got the exact same answer that we got. They got 0.4650. We got 0.4650. Yeah, actually. It rounds to the exact same number. This problem combines the idea of a probability tree and a binomial. You just have to be able to separate the two and properly interpret what the question is asking. And again, if you look at their probability tree was not as detailed as mine. I like mine better. But that's what they got. Okay. That's going to be it for today. If you have any additional questions, make sure you email me. And of course, I will be back again tomorrow with the 3rd review that we can do before this test. And hopefully we'll see you then.